Hey there, and welcome. I'm Naya. Today, you're not just a student, you're a detective. We're going to crack the case on chemical reactions, learn how to spot clues, analyze the evidence, and solve some of the biggest mysteries happening right under our noses. All right, ready? Let's dive in. So, our first case file opens in the kitchen. We've all done it, right? You leave the milk on the counter on a warm day, and when you come back, something's just off. The smell, the look, it's completely changed. This is our first crime scene. But what or who is the culprit? And here's another one for the file. You leave a cast iron pan out where it's a bit damp. Next thing you know, you've got these reddish-brown spots popping up all over it. Rust. The pan's very identity has been changed. Now, these two things, sour milk and a rusty pan, seem totally unrelated, but they're connected by a very powerful secret. So, what is it? What's the secret force that links these everyday events? Well, in both cases, the original substance is going through a total transformation, right down to its molecules. And your job, detective, is to figure out exactly how and why.
That's right. You are about to get the training you need to see the world through the eyes of a scientist. So you might want to grab a notepad because your training as a chemical detective starts right now.
First things first, every good detective knows that before you can even think about solving a case, you need to know what you're looking for. It's all about spotting the signs, the clues that a chemical event has even happened. The official name for the event we're investigating is a chemical reaction. You can think of it as a process where our original substances, our suspects, if you will, are transformed into something completely new. And that's the key here. Something new gets created. So how can you be sure a reaction has actually taken place? Easy. You look for these 4 telltale clues. Consider this your standard issue detective's toolkit. If you see a change in state, a change in color, bubbles of gas appearing, or a change in temperature, you're definitely onto something big. Now check this out, because this is a great piece of evidence. When a magnesium ribbon burns, you're seeing 2 clues for the price of 1. It starts as a solid metal strip, and it ends up as a white powder. That's a change in state and a change in color. Talk about a dramatic scene. Okay, on to our next clue. When you drop little pieces of zinc into acid, you immediately see all these bubbles fizzing up. That's a gas being created right there. In our detective lingo, we call that the evolution of a gas. And trust me, it is a dead giveaway that a reaction is in progress. And believe it or not, that exact same experiment gives us our final clue. If you were to actually touch that flask while the zinc and acid are reacting, you'd feel it getting warmer. That release of heat, that change in temperature, is your 4th and final sign. And just like that, you have all the tools you need to spot a reaction. All right, detective, you've spotted the clues, you've confirmed a reaction took place. Now it's time to file the report. In chemistry, our official case files are called equations. It's how we write down exactly what went down. In every case, you've got 2 key players. On one side, you have the reactants. These are your initial suspects, the substances you start out with. And on the other side, you have the products. That's the outcome of the investigation, the brand new substances that were formed. The easiest way to write up the report is with what we call a word equation. We put the reactants on the left, then an arrow to show that a change happened, and finally the products on the right. So for our magnesium case, the report reads, magnesium plus oxygen reacts to form magnesium oxide. Simple, clear, official. Case closed. Okay, time for a quick pop quiz to see if you've been paying attention. Look at this equation. Zinc plus sulfuric acid yields zinc sulfate plus hydrogen. Your mission, identify the reactants. Who are our initial suspects here? Got it? If you said zinc and sulfuric acid, you nailed it. Excellent work. All right, listen up, because this might be the most important part of your entire training. There is one golden rule in our line of work, one unbreakable law that governs every single reaction you will ever investigate. And here it is, the law of conservation of mass. What it means is simple. You can't just create stuff out of thin air, and you can't make it disappear into nothing. Every single atom you start with has to be accounted for at the end. There are no exceptions to this law. So what does that mean for our case files? It means that for an equation to be legit, the number of atoms for each element has to be exactly the same on both sides of that arrow. Nothing gets lost, nothing gets gained. And this brings us to our final and most advanced detective skill. Welcome to the final stage of your training, detective, balancing the evidence. This is where the real puzzle solving happens. We have to make sure our case files are 100% accurate and follow that unbreakable law we just talked about. Let's pull up an unsolved case. Here we have iron, that's Fe, reacting with steam, H2O. The result is a type of iron oxide and some hydrogen gas. But as it's written right now, this report is totally unbalanced. The evidence just doesn't add up. Let's do a quick atom count. On the left side, we start with 1 iron atom, but on the right, we somehow end up with 3. And look at oxygen. We start with 1 atom on the left, but end up with 4 on the right. This case file would get thrown out of court. We've got to balance it. We're going to use something called the hit and trial method. It's basically just a logical step-by-step process. First, let's focus on the most complicated-looking compound, Fe3O4, and start with the oxygen. We need 4 on the left, so we'll put a big 4 in front of H2O. Okay, good. But wait, that messed up our hydrogens. No problem. Next, we just put a 4 in front of the H2O on the right side. Now they're balanced again. And for the final step, we need 3 iron atoms on the left, so we just add a 3 in front of Fe. And there you have it. Case file solved. Let's do a final check. 3 iron on the left, 3 on the right, 8 hydrogen on the left, 8 on the right, 4 oxygen on the left, 4 on the right. It's perfectly balanced. The evidence adds up, the report is accurate, and the law has been upheld. Well, you've done it. You learned how to spot the clues, file the report, and balance the evidence. Now it's time for your final exam. This is it, your first solo case. Okay, here's the scene. You walk into the lab and see 2 beakers, each with a clear, unknown liquid inside. They look exactly the same. Your mission, should you choose to accept it, is to figure out which beaker contains an active chemical reaction, using only your powers of observation. So, you carefully approach the table, you touch the beaker with liquid A. Nothing. It feels like room temperature. But then, you touch the beaker with liquid B, and you notice it's warm. It's definitely giving off a little heat. So, what does this single clue tell you? If your detective instincts told you that liquid B is where the action is, you cracked the case. That change in temperature is one of our 4 key clues. You just used your training to solve a real mystery. Congratulations, detective. You've graduated. Now that you have these skills, I promise you're going to start seeing chemical reactions everywhere. So I'll leave you with one last case to ponder. Photosynthesis. A plant takes sunlight, water, and a gas, carbon dioxide, and turns it into solid sugar. You've got a change of state, and you're creating a totally new substance. It's one of the most important reactions on the planet, and now you know how to look at it like a detective. And that's all for this investigation. If you had fun during your training, make sure to like, share, and subscribe for more explainers. Until next time, keep those eyes peeled for clues and always stay curious.